A key value store is a non-relational database because the data is not organized in rows and columns like in a relational database. If we had a relational database for an e-commerce app, we would have a table having rows and columns, and this table is called the users table. And then we can have another table that is used for storing the products. Whenever a user buys a product, we store their record in the products table and link these two tables or records. For example, if we have a column called ID in the users table and we have a column called UID standing for user ID in the products table, and we have about 1, 2, 3 users. In case a user with ID 3 buys product, we can put their record in this row and say this user has bought a product. Or on the next row with 1, meaning a user with ID 1 has bought a product. And this creates a link between the ID column in the users table and the UID column in the products table, hence creating a relationship. So this is how these two tables relate, hence a relational database. This is how simply I can explain relational databases. But key value stores are non-relational. Have this in your mind, which means they do not follow the structure of rows and columns and are not connected or linked using keys. Have this at the back of your mind. They are non-relational. So let me clean up this space and explain what I want to share with you. Now, the next thing you have to understand is that the term or the word key value store actually defines what they are. The first word key refers to a unique identifier. This unique identifier is associated to a particular value. So you have a key, and this key is associated to a particular value, and both of them are called a key value pair. A key combined with a value or a key associated to a value is called a key value pair. And a key can be either plain text, have this at the back of your mind, or a key can be a hashed value, meaning this hashed value is given to a function that takes in a chunk of text, and this function then produces random characters known as a hash. If we give a particular piece of text to this function called the hash function, it should produce the same hash every time. So the key can either be plain text or a hash. Keep this at the back of your mind. And this key, like I've mentioned, is a unique identifier. It helps you to fetch a value that you want. For example, you can say city is a key. Maybe let me use a different color. We have city as a key, and then the value is Nairobi. This is an example. And the value in this case can be anything. You can have this value as a string. This value can be an object. This value can be an integer or anything else. Literally, you can store anything. And for the keys, try to keep them as short as possible for performance reasons. So the goal is going to be to design a key value store that can perform the following operations. The first one will be to do a put operation, and put will involve being given a key and a value. So you supply a key and a value to put, and this key and value will be stored in your hash map so that later you can do another operation called the get operation, and this get operation will be able to retrieve for you the value given key. So for the get operation, what you need is only to provide the key and you'll be given the value that you need. So think of it as a simple data structure that is going to help you to store data based on the keys. And the keys, like I've said, are unique identifiers. Now, What you're seeing me draw is simply an illustration of how you should picture it in your mind. Assuming maybe we had a key 1, 2, 3 with the value A, B, C. It can be anything. Maybe you have a value called, not a value, but a key called edge, whose value is probably 1, 2, 0. You have another value, maybe name, not a value again, but a key called name, and the value is maybe YT, okay, for YouTube. This is how you can picture a key value store. Let's go ahead and understand the problem we have at hand and what we need to think about. One thing I need you to understand very well is that system design is about trade-offs. Every design chooses between a number of trade-offs. In this video, when designing the key value store, we're going to look at trade-offs between read, write, and memory usage. Another trade-off will be between consistency and availability. If you're new to the concept of consistency and availability, I encourage you to read about them or watch the videos in the playlist to understand trade-offs properly. It will help you understand how we're going to design the key value store. Then something else you need to know is that this key value store is going to have a number of characteristics, and I want to list them out one by one. So it will be characterized by the following. The first one is that we need a key pair which is small. Key value pair which is small. Maybe you can simply say a small key value pair. And I'm looking at sizes of less than 10 kilobytes. Then after that, we need to be able to store so many key value pairs. So I'll say store big data. Simple as that. Then the next one should be that our system should respond quickly even during failures, and that is high availability. Then the other characteristic will be that when the data increases, we want our system to be able to be scaled up. So the next characteristic will be high scalability. After that, we want that when you add a server or when you remove a server, I want automatic scaling. And then we want the consistency to be configurable. Then we want things to happen with low latency. Let's now talk about a single server key value store. Designing a key value store in a single server is actually quite easy. All you need to do is to store your data inside the hash map. So this hash map lives inside memory. So I'll call this little green box a hash map, and I'll simply label it as an H map. This is something I like to do even in code. I call my hash maps H maps or Python dictionaries most times when I'm trying to solve data structures and algorithm problems. Anyway, away from that. So when you have this hash map and you store your data inside it, you have fast access because it's working in memory. But the challenge with that is that the memory gets filled up very soon. That gives you a space constraint. And you can try to optimize it by trying to compress data. Okay. One trick is to compress the data. Not a trick, but an optimization strategy would be data compression. But compressing data can only take you a long way. At some point, you'd run out of space still. You may even think of another optimization technique and say, I will store some data which is frequently accessed in memory, and then the rest of the data, I'll store it on disk. Okay, so that if in case it's required, I can fetch it from disk. And then that is frequently required, store it in memory. Something which is not frequently required can be fetched from disk into memory. But either way, you still hit the limitation of space on this single server. So the solution is to move to a distributed key value store. And that's what we're going to talk about in the next section. A distributed key value store can also be called a distributed hash table. What this means is that the key value pairs are stored across many servers. So I'll just draw a few diagrams here. So this is server N1 or node 1. I have another node called N2 and another node, I'll call it N3. So don't cram that there are 3. They can be 2, 4, 5, 6, depending on what you're trying to achieve. So when we have these nodes, and these nodes are storing our key value pairs, this is what I refer to as a distributed key value store. But this key value store is going to be designed around what is called the cap theorem. And I'm going to explain to you what cap theorem is all about. It's actually an abbreviation. I want to drag this. I don't know why it's becoming stubborn to drag. I'll copy that and then drag it down. So let's talk about cap theorem. To design a distributed system, you must understand the cap theorem, and I'll explain it. The C in the cap theorem stands for consistency. Okay, so the C stands for consistency. I don't know why the color has changed. Let me just make sure it's what I intended to be, and then we can continue. So the C stands for consistency, and then the A stands for availability, and then the P stands for partition tolerance. So what does consistency mean? The C, or consistency, means that in a distributed system, all clients or a client must see the same data or the most recent data, no matter what node they connect to. So if you have a client and this client tries to access data from node 1, they should see the most recent, right? They should see the same data if they try to access it from node 3. If the client is connected to node 2, they must see the same data. If we have another client, probably from another region, trying to access data, and this client is connected to node 3, they should see the same data that the client on this other end sees. So I'll call this client client A, and this other one will be client B. So if client B and client A are connected to node 3, they must see the same data. If client B is connected to node 2, but client A is connected to node 1, they must also see the same data. And the record they want to find out is the same. No matter the node they are connected to, they must see or access the same data. Okay, let's move on to the A. In case you have a question, leave it in the comment section. Now, for the A, I want to erase these other things very quickly and go on to the A. A stands for availability. For availability, it simply means that when a client is connected to our system, by the way, all these nodes make up one system. They're not individual, okay? They all logically create one system. So for availability simply means that when a client connects to this single one system, and in this system, maybe there are some nodes which are down. Let us say node 3 is down. So availability simply means that clients or a client gets a response even if some nodes are down. That's what defines availability. Simple as that. Consistency, clients see the same data no matter what node they are connected to. For availability, a client must get a response even if some nodes are down. Now, let's talk about the P. P stands for partition tolerance. But to understand partition tolerance, you need to understand what a partition is. In networking, when one node cannot communicate with another node, that is said to be a network partition. In the event that a network partition happens, then the system must be partition tolerant, meaning the system must continue to operate even when there is a network partition. As simple as that. And this cap theorem states that it is impossible to achieve all the 3 in a distributed system. You have to sacrifice one of these 3. So you can only have 2 out of these 3 properties. The key value store can either be designed as a CA system. So a CA system means that we are choosing consistency and availability and sacrificing partition tolerance. Have that at the back of your mind. If we choose to go with an AP system, it means that we are choosing availability and we are choosing partition tolerance, but we are sacrificing consistency. Think about that. Then, if we choose a CP system, it means that we are choosing consistency and partition tolerance and sacrificing availability. In an ideal world, you'd assume that you're going to have a CA system, a consistent and available system, but it is impossible in a real world because partitions always occur. It is very difficult, okay, or say impossible to achieve a consistent and available system because network partitions must occur and they actually always occur. So because network partitions are inevitable, they are just waiting to happen, we must choose between an available and partition tolerant system or a consistent and partition tolerant system. That is what we have to choose. So we're going to choose between AP, CP, and forget about the CA. Why? Because network partitions are inevitable. Now let me explain this a little bit deeper. If we go down here, and I'll just paste the same diagram, a 3-node system or a 3-server distributed system for our key value store. And imagine you have an ideal situation where you're trying to achieve the C and A, consistency and availability, whereby when you write to node N1, you have that data replicated to node 3 and N2 successfully. But remember, that is only in your imagination, I would say. It's not really true. In the real world, network partitions are inevitable. So let us assume that N3 suffers a network partition. And because of this network partition, we cannot communicate with N1 and there's no communication with N2. And then you try to write data to N1. Because of that, N1 will only replicate the data to N2, but N3 will not have that data. That's an issue. If you try to write to N3, N1 and N2 will have stale data. I think now you understand better that achieving CA is quite impossible in a distributed system because of network partitions. Now, let's look at the AP and CP. If you wanted to achieve CP, consistency, partition tolerance, and for example, you made a write, okay, and the data went to N1. Because you have a network partition, you would block or stop that write operation because you'd want all nodes to have that data, okay? Because remember, you want to achieve consistency, but then you have a network partition. So all write operations are stopped until every node is okay. Then, if you need to achieve the AP system, in that case, if you wanted to do a write operation, okay, you would write to the nodes which are available N1 and N2, and then later, but when this network partition is resolved, then you can replicate the data to N3. The challenge with that is that there's a chance you see stale data. So every time you design the systems, you have to choose, what am I sacrificing? Okay. Is it availability? Is it consistency? Think about all these things. It's very, very key. Now let's talk about the components of our key value store. Let's talk about data partitioning. For large applications, you don't want to store all the data in a single server. What we want to do is split the data into multiple partitions and then store them in multiple servers. But while doing this, there are two challenges that we need to think about. The first one is that we need to distribute the data evenly across the multiple servers. Then the other challenge is that we need to minimize the data movement when we are removing a node and also when we are adding a node. Thankfully, there's a technique which can help us address this issue, and that is consistent hashing. So I'm going to explain to you at a very high level what consistent hashing is all about and how we can partition data using this technique of consistent hashing. It's actually very easy to understand, and trust me, it is powerful enough to help us address this challenge. Now, let's talk about consistent hashing. We are going to think about a system having a number of servers, and this will be 8 servers. And the servers are going to be placed on a hash ring. So think about a logical hash ring. So I'll draw a circle here. So this circle will represent a logical hash ring. And the servers are going to be placed on this hash ring, about 8 of them. So let me draw each of the servers. So this is the first server. I'll call it server 0, S0. Okay, then we shall have another server here. This is the second server. Then we have the second server. Then we have the third server. Then we have another server here. Then we have the 60th server. Then we have the 7th server. And then we have the 8th server. Is this the 8th or the 9th? This is actually supposed to be the 8th. The numbering confused me. So the one coming before right here is supposed to be S6. So these are 8 servers placed on a logical hash ring. So the next thing to do is that we hash a key onto the same ring. So I'll pick a different color and just draw a small circle here that is dashed. So this is a ring, and we are now hashing a key onto the same ring. And I'll call this key, I'll say key 0 to denote the first key. So we hash a key 0, on this hash ring. And then this key is stored on the first server encountered while moving in the clockwise direction. So clockwise direction would mean moving from S0 in this direction like this. How you're seeing me drawing this arrow. Anti-clockwise would be the opposite, whereby you start from S0 backwards in this other direction. So we are going to store this key that has been hashed on the first server encountered while moving in the clockwise direction. And in this case, S1 is the first server we meet when moving in the clockwise direction. So this key is stored on the first server S1. As simple as this. Now, consistent hashing to partition data has a number of advantages. The first one is that it helps us to automatically scale. Why? Because we can easily add a server and easily remove a server automatically depending on the load. Then the other thing is that it helps us to have servers with a higher capacity being assigned with more virtual nodes. Or simply to say is that the number of virtual nodes for a server is proportional to the server capacity. As simple as that. Now, in the next section, we're going to talk about data replication. If you need to digest this, I would suggest you to pause and think about this, and we're going to build on this until we get into all the techniques and concepts of how our distributed system is going to work. See you in the next section. I will use the diagram from the previous section to explain to you how data replication can be handled. Now, to achieve high availability and high reliability, data must be replicated asynchronously over n servers. So what is n? N is simply a number which is configurable. Think of it as a configurable parameter which tells us the number of servers. So at some point we can have n being equals to 7, or n being equals to 9, n being equals to 5, or anything. Let's say n in this case is 3. Now follow me closely. Just like in the previous section, we hash a key, okay, onto this hash map. Not hash map, but hash ring. And again, it's a logical hash ring. Then after this key, I'll draw a simple filled-in circle to represent this key, which has been mapped to a position on the hash ring. So after this key has been mapped to a particular position on this hash ring, we walk in a clockwise direction. And The goal is that as we walk in the clockwise direction from the position where we have hashed this key onto the hash ring, we then choose the first n servers. So in this case, n being 3, we shall choose S1, we choose S3, and we choose S3 rather, okay? This one was S2, but I called S3. So we choose S1, S2, and S3 as the servers where we shall store our data copies. So S1 will have the first replication or data copy, S2 will have the next data copy, and S3 will also have the other data copy. If n was equals to 4, then we'll go on to hash, not to hash, but to store our data on this other server. Now, in the event that we had virtual nodes, the first n nodes on the ring can be owned by fewer than physical servers. Why? Because one physical server can have maybe 2 or n virtual nodes. So to avoid this issue, we can choose only unique servers while performing the clockwise logic. Okay? Understand that. Now, if you have a question, of course, leave it in the comment section. Now, let's go on to something that I want you to know. And I think I've mentioned it in this playlist or in other videos. And the issue here is that when you have your nodes in the same data center, they can fail. Why? They are prone, okay, not prone, but there are challenges that can affect your data center, like a power outage. You may have a natural disaster, like maybe an earthquake. You could have network issues. Anything can happen. Now, for better reliability, the replicas can be placed in distinct data centers. And these data centers are connected through high-speed networks. Now, let's move on to the next section where we're going to talk about consistency. Let's handle consistency in our distributed key value store. For this to happen, the data, like we know, is going to be replicated across multiple nodes, and it must be synchronized across these replicas. For that to happen, we are going to have a quorum consensus to help us guarantee consistency for both write operations and also read operations. I'm going to use a similar diagram that I've used in the previous section. So I'll draw the circle. Let me try to make it a little bit bigger. And this time I'll say we have a number of maybe 3 nodes. So a node S0 at this position doesn't really matter. This is just to ideate it and make it logical to you. Then another node here, I'll call it S1, and then another node S2, and I'll have here a coordinator which will be responsible for coordinating the read and write operations between all these nodes. Okay, so I can just put here a number of arrows just to show that there is communication between the nodes and the coordinator. So each of them has to communicate between themselves and the coordinator. So that's what these arrows show, that there is continuous communication. So I can label this and say this is the coordinator machine or server in our setup. Now, to understand how this is going to work and how the quorum consensus is going to work, I'm going to define a number of terms. So the first one is n. Think of n as the number of replicas. I need the brighter color for this, so I'll just put it here. N is the number of replicas. Then W will be the write quorum of size W, which means that for any write operation to happen and for it to be considered successful, the write operation must be acknowledged by W replicas. Okay, and I'm going to touch on this more. Then we're going to have another one called R, and R will be the read quorum of size R, meaning that for a read operation to happen and to be considered successful, read operations must wait for responses from at least R replicas. Let me explain this further. Now, according to this diagram, we see that n is equals to 3. N is equals to 3. Why? Because we have S0, S1, and S2. Only that. So n is equals to 3, meaning the number of replicas are 3. After that, I want to define W. If, for example, W is equals to 1, okay, it means that the coordinator must receive at least one acknowledgement before a write operation is considered successful. Again, W is for write. So, meaning this coordinator must receive at least one acknowledgement, which means if data is written to S0, it must get an acknowledgement from either S1 or S2 for that operation to be considered successful. So if we write data to S0 and the coordinator gets information from S0 that, okay, I have written data successfully, then if S1 confirms that it has also written the data to itself, then that write operation is considered successful because we have one more node which has confirmed that. If W was equals to maybe 2, then we'll need the confirmation from S1 and S2. Understand this and all will be clear. Of course, like I already said, if you have any question, please don't hesitate to ask and leave a comment in the comment section. Now, let's go ahead and talk about these configurations even at a slightly deeper level. It may be deeper, but not even that complex. Just giving you more, can I call it intuition or more thoughts on what I think this should be from my learnings. Now, if we get acknowledgement, like I've told you, from S1, okay, after a write was made to S0, we don't need to wait for acknowledgement from S2. Why? Because W is equals to 1. All we need is one acknowledgement. And by the way, in system design, you'll find most people defining acknowledgement as ACK. Okay, so it is simply short form for acknowledgement. So when you meet ACK anywhere, just know that the node needs acknowledgement. You don't have to always have your configuration stacked to 1. These values, okay, can be configured. So after your W equals to 1 has been confirmed and is done, you can now wait for another request. Or later you can change the value of N, the value of W, you can change the value of R. So it's all about handling trade-offs, okay? And at this point, we are looking at trade-offs between latency and consistency. Think about this. If W is equals to 1 and R is also is equals to 1, an operation can be returned quickly because the coordinator now needs to wait for a response from any of the replicas. But if you have these values, okay, of W and R greater than 1, so if W is greater than 1 or R is greater than 1, then the system offers better consistency. The only challenge that you may have slower queries because the coordinator must wait for response from the slowest replica. Now, something else I need to touch on is this. If W plus R is greater than N, so meaning the write consensus and the read consensus is greater than the number of nodes, then you have very strong consistency, which is being guaranteed because there must be at least one overlapping node that has the latest data to ensure consistency. So I think you see how that these things can be configured and you can adjust it to fit a particular use case. Now, think about this. What if R is equals to 1 and then you have W equals to N? What will the system be optimized for? Think about it. It will be optimized for a fast read. You get, because you only need one read consensus, but you need N read not read, but n write consistencies. Okay, so this is much slower. You must get confirmation from n nodes. Then if w is equals to 1 and then read is equals to n, it means the system is optimized for a fast write. You need only one write consensus, but you need n read consensus. Then again, if we have w plus r being either less than or equals to n, then you have a situation whereby strong consistency is not guaranteed. So depending on the requirement, like I've already told you, think about these trade-offs. You can then tune the values of R, W, and N to achieve the desired level of consistency. Now let's talk about consistency models I've talked about in the past. To design our key value store, we need to understand consistency models, which I've talked about in this playlist, but I know some people might be watching this video for the first time. So I'll go ahead to talk about them very briefly. The first one is weak consistency. Why is it called weak consistency? It's because read operations may not see the most updated value. A client can ask for data, but the data they are seeing is not the most recent write. The other one is called eventual consistency. So eventual consistency is actually a kind of weak consistency whereby the data is stale but only for a particular time. If you give enough time, all updates will be propagated to all replicas and they will be consistent. Then the other one, which you might have guessed, is called strong consistency. So for strong consistency, any read operation returns a value which is the most recent write, which means that a client never sees out of date data. So consistency is achieved by forcing a replica not to accept any new read or any new write until all the replicas have agreed on the current write. In the next section, we're going to look at how to handle inconsistencies. I will explain how to resolve inconsistencies using a diagram. Let's say we have two replica nodes. This first one is called N1 and we have a second replica node called N2. These nodes store a name of a place. I'll say the name is probably, I'll call it India. And both of them have the same correct original value. N2 also stores a value which is India. Then these values are accessed by two servers. I'll have a server on this other end called server 1, and server 1 performs two important operations. So let me draw it. So this is the first server. I'll call it server 1, and maybe I should make this bigger or smaller so that the words can fit. And then we have another server called server 2. And both of them perform the same operations to, number 1, request for data from the replica nodes. Server 1 can perform a get operation. Remember, we are still talking about our hash table, our distributed hash table. Can make an operation to say get the name. Maybe I should use a different color for this. Get, what we want to get is the name. So when server 1 performs an operation to get the name, the result that they should be given should be the name. So the value returned will be India. As simple as that. Return India. In the same way, when the second server makes a get operation for the name, the return value will be India. So India is now the original current value that we have in our distributed key value store, having two replica nodes. Now, what if server 1 now performs a put operation? So it says put, no putting is simply updating the value. So we want to say this time name would be a different country. You get? Maybe it will be Kenya. So that means we now don't have India anymore, but we have Kenya. Follow me closely. Then after that, we have server 2 also doing the same put operation and changes the value from India to something else. Let's say it's Turkey. Server 1 and server 2 perform put operations and it results into a conflict. Now we ask ourselves, what is the solution to this? What is the truthful value? Is it Kenya? Is it Turkey? You get? This is what a conflict is. Now, the goal of this section was to explain how we resolve and solve this conflict. To solve it, we're going to use a technique to be able to detect conflicts and to be able to reconcile these conflicts. The technique is called a vector clock. So we're going to use a vector clock to help us detect the conflicts and then also reconcile these conflicts. It's a very simple concept and you're going to understand it. A vector clock is simply a pair which is associated with a data item. Let me explain. I said it's a pair associated with a data item. So what kind of pair is it? It is simply a server and version pair. Follow me closely. A server and then a version makes up a pair. And the goal is simply to determine that a particular version either precedes. If it does not precede, then the version could probably succeed others, or the version could be in conflict with others. How would these pairs or pair look like? The data item, okay, can be represented by a letter D. So I'll say D for data item. Maybe let me use a different color. So D is representing a data item. And this data item is then written to a node. When it's written to a node, we track the server. Okay, for example, it is server S1. And we also track the version. Maybe this is version 1. We can have another one, server 2, holding the second version of the data item. We can have another one, server 3, holding maybe the third version, and so on and so forth, for any number of servers and for any number of versions. So N here represents any number of servers, and N also here next to the V represents any number of versions. So just have it in your mind that S represents a server and then the V represents a version. And I'm going to make sure I explain this even better. How do we use this to solve inconsistencies? Before we even go into that, understand that when a system, and this is a distributed system, wants to perform something, okay, not just something, but if a system wants to write data in our system, if a data item is to be written to a server, then our distributed system must perform one of the following tasks. The first task is to increment the version. I'll call the version VI, where I could be any version, maybe version 1, version 2, version 3, version 4, anything. And the increment only happens if a data item exists. So I'll say if a data item SI, VI exists. So S again stands for the server, V for versions, and I means it could be any server, and VI means it could be any number. So if a data item exists, for example, we have maybe server 1 and the version number is 3 of the data, then we increment it to this, to the next one, to 4. That data version is added. Otherwise, if it does not exist, then we simply create a new one or a new entry. The particular server SI has its first version, which would be version 1. Understand this, and it will make things easier for you as I go on. Now, earlier here I had used V3, v4, but you can simply say this is just 3. Okay, this is just 3 and this is just 4. That also makes sense. And these are not i's but ones to represent a server number. Now, let me get into a better example to explain this even more. Let's say we have a server, or servers actually, because we can't be talking about a server only in a distributed system. We must have a number of servers, and these servers are accepting client requests. So let's say a client writes a data item, and this data item will be called item D1. Let me use different color. So item D1 is simply a data item. And this data item, like I showed you earlier, simply has the server number and the version. So let's say this item has a certain server called server X and the first version, which is 1. So the request comes from the client, and this request is managed by a server called SX, and we track the version as version 1. Follow me closely. After that, we have another client which reads this latest value or this latest data item called D1 and updates it to D2. So a client sends another request, and we have this same data being modified and being handled by the same server. So we have the same server SX updating this data item now to version number 2. Very simple, right? Now, another client reads this version that we have, the latest version called D2, and updates it to D3 or to data item 3. So I'll come here and say we have here data item 3, and this time it's being managed or being processed or handled by a different server. I will call this server SY. So I'll make changes and I say this data item. Remember, it is D2 being changed. So we have a transition from this other one, okay, the previous one, which is D2, to a new version, which is being handled by a new server SY, okay, and the current version is now version 3. This first part comes from this version here, okay, and then this one is the update. After that, we have another server. I'll call it server SZ. So this other server also updates D2. And D2 now, we can call it now D4 because this is a new data item. And this data item is now changed from its state of SX and version 2 now to a new version. Okay. Actually, I made a mistake. Server SY, look at this, cannot have version 3 because this is the first instance it has. Forgive me for that. I will change this to 1, okay? Because this version 2 here is from server X. If server X was handling the right operation here, we would have this as 3 and not 1. But server X is not the one doing it. It is server Y. So if it was server X, we would have this as 3. Then let's go back to the side. We have another server which reads the data, okay, from the client rather. The client reads the data from D2 and updates it to D4 and writes it back. And this write is handled by another server. And this server is called SZ or Z. And this server SZ has now its first version of this data. And this is how the vector clock works. Now, what happens when another server tries to make a request, not a server but a client. When another client now comes into play and reads D3 and D4, it sees that there is now a conflict. It is caused by data item D2 being modified by two separate servers, server SY and server SZ. Those are the servers that interact or modify or handle the rights for the client requests when the original source was D2. So we have a conflict. So what happens to solve this? The conflict is then resolved, okay? The client sees this conflict and resolves this conflict. After the client resolves this conflict, data is updated and sent to the server. We can assume that this update is handled by server X. So we have server X working to resolve the conflict from D3 and D4. Maybe I can continue using the white color. We have a server SX handling the conflict resolution from D3 and D4. Remember, D3 and D4 were written by server X and server Z. So now the new data item D5 would be this. We have the value from, what can I call it? From SZ and SY. Okay, we have the value from SY and SZ being looked at because those were the most recent values we had from D3 and D4. And then server SZ, which is now handling this write operation, finally has the reconciled value, which would look something like having SX, okay, having version 3, okay, which is the latest. And then we have another one, SY version 1 from the previous step. And then we have SZ with its version. If you follow me closely, this makes sense. Of course, if you're confused, please let me know in the comment section. So this is how the whole resolution comes about. But I want to explain it even better. How do you detect a conflict? Now, let me explain to you how to detect conflicts. You can tell that a version X is an ancestor, or meaning it has no conflict, of another version Y if the version counters for each participant in the vector clock of Y are greater or equals to the ones in version X. For example, if I have a vector clock like so, where I have S0 and then S1, okay, and then have this other one S1, okay, and then maybe I should make this smaller for it to make sense. And then we have another here, and I can close this. You have this, okay, and it's an ancestor of this other one here. So maybe I can just copy this whole thing and make a copy. So maybe I can erase, make my point, I can erase this value, and I can also erase this other value. So I explained to you what I meant. So here I have a 1, should have kept it, but here I have a 2. So this other one which I've circled in yellow is an ancestor of this other one. Now, once you see that the vector clock of this one here, which is Y, I'll call this one X, okay, is greater than or equal to the one in the version X, okay, then you know that there is no conflict, okay. This is good days, there is no conflict. But you can tell that there's a conflict in case a version X, okay, is a sibling of Y. And if you see that there's any participant of Y's vector clock who has a counter that which is less than its corresponding counter in X. I'll show you an example. Just make edits to the same vector clock and then show you the changes. So here we have S0, S1, we have here S1, but this time instead of this 1, I'll put here a 2, okay? Maybe I'll just use white. So then down here, this one I'll make it 2, and then this other one I'll make it 1. So I want you to look at the values. I said you can tell that a version X is a sibling of y if a participant in y's vector clock has a counter which is less than its corresponding counter in x. And this is a perfect show. Okay, look at this situation. Look at this one and look at this 2. Okay, this one is less than. So this kind of situation, it looks like x is a sibling. Why? This value in y is less than this one here. So there exists a conflict. That is how you detect conflicts in a vector clock. But now the challenge is, once you have all these working, okay, it is a little bit complex, like you've seen. And this complexity falls on the client. Client has to be able to resolve these conflicts successfully. And the other issue is that these pairs, okay, the server and version pair grow very rapidly, especially in a system where you have a lot of reads and writes. You can fix this problem using a threshold, okay, and say maybe when we have maybe about 200 pairs, then we can remove the old one. Maybe the first 50 can be deleted, depending on what you want to do. And that can, of course, easily lead to inefficiencies in reconciliation, because now the descendant relationship cannot be determined accurately. But from some of the things I've been studying online, it is said that Amazon did not encounter a problem in production using this kind of setup, using a vector clock. So it might be something acceptable for your use case too. That's it on how you can handle conflict resolutions. Let's talk about how to handle failures. To handle failures, the first thing we need to implement is being able to detect a failure. That's the very first step. And to detect a failure, we shall use a protocol called gossip protocol. And this is how it's going to work. Every node is going to have what is called a node membership list. It will comprise of the member ID, which is simply the ID of a node, and then it will also have the heartbeat counter, as simple as that, including the time when this heartbeat was registered. And after that, we can use this information to detect failures. I'm going to show you how this is going to work. Now, every node, like I've said, will have this kind of information. The ID of a node, for example, can have node with ID 0, node with ID 1, 2, 3, and so forth, depending on the number of nodes that we have. And remember the ring that we had earlier on still exists. Do not forget about it. And at this point, let's say we have a node S0. Okay, so S0 and another node S1 and another node S2 and another node S3. Of course, earlier we had 7. I just want to keep it simple by having 3. So these 3 nodes will have their information stored like this in this table. And S0 will have a copy of this information. S1 will have the same copy. S2 and S3 will also have their own membership lists. Now, let's say we want to detect a failure from S0. Okay, so S0, but even before that, generally the whole idea is this. Every node has this membership list and updates its bit counter in this table. Okay, think of it as a table, logical table. And then it sends its information to every other node that I have updated my list as follows. Have my information so that every other node also updates its own self. So let me try to populate this table with some information and then I'll explain something to you. So let's say maybe the heartbeat of node 0 is 100. Node 1 is probably 10, maybe 3. Node 2 is maybe 70. Then the next node would be node 3 and its value is 1, maybe 0, 1. And the time, maybe this one happened at 11, maybe 5, 9. This one, maybe 12, 00. And then we have this one here, maybe 10, 00. And this one here happened at 12, let us say 01. So I'm going to use this to explain the rough concept. And this table is for S0. Okay, but keep in mind that all these other nodes have the same node membership list. So node 0 notices that node 2's member ID, okay? Node 2's member ID, or node 2 simply, which is this row. Let me highlight with a different color. So this is the row we're interested in. It says that this row actually is lagging behind. The heartbeat counter has not been increased for a long time. Why? You see the heartbeat is stuck at 70 while these others are ahead. It also says that the time it was last updated is way back. Okay, so node 0 sends heartbeats that include S2's information to a set of random nodes. Maybe it sends that to node 1, S1, and node S3. When it does this, S2's information that it has not been updated for a long time is then also noticed or confirmed by S1 and S3. So once these other nodes confirm that yes, it is true that also our tables or our membership lists are indicating the same thing, then node S2 is marked as down, and information is also propagated to other nodes. That is how the gossip protocol works. Each node maintains a node membership list which contains member IDs and heartbeat counters. Then each node periodically increments its heartbeat counter, and then every node sends its heartbeats to a set of random nodes, which in turn also propagate that information to other nodes. So once a node receives its heartbeat or heartbeats, the membership list is updated to the latest information. Now that we know how to detect a failure, let's look at how to handle the actual failure once it has been detected. We used the gossip protocol to detect a failure. Now let's handle the failure, and we shall start with temporary failures and then handle the permanent failure later. The system that we're working on must be able to establish the number of servers which are healthy for writes and those which are healthy for reads on the hash ring. We can say maybe W is the number of servers which are healthy for writing. They are the fast health servers. And then R will represent the fast servers which are ready for read and write operations. But let's imagine that in our simple setup with these few servers, if a server, let's say, is unavailable because of a network issue or because the server has encountered the failure on its own, another server has to pick up and process all the requests temporarily. I'll give an instance with what we drew in the previous section. Server 2 is currently down. So what can happen is that server 1 or S1 takes charge of the read operations and the write operations. And then when this server S2 is back up from its failed state, it can now handle operations. Server 1 hands the data back to it, and then everything can go on as usual. This is how we can handle temporary failure. Let's look at how to handle permanent failures. To handle permanent failures, we shall use a Markov tree. A Markov tree is also called a hash tree, and it's a type of tree in which every non-leaf node is labeled with the hash of the labels or the hash of the values of its child nodes. And I'm going to show you how to build one. Now, let's assume we have a key space ranging from key 1 up to 12. And we're going to build the Markov tree step by step. The first goal is to divide the key space into buckets. Let me create them. So we shall have right here the first bucket, and this bucket will have following keys. I'll say the first key, then we have the second key, then we have the third key. I don't have to divide this anymore. I just put 3 here, and then I can duplicate it a number of times. The first time, then I have another copy made, then plug it right here. And with this, we have a number of copies, but I need one more so that we have 4 buckets. So let me copy, duplicate this, just drag it to this side. So this is the key space, but I have to rename a number of keys starting from the second one. So I can quickly erase this too, erase this other one too, and then say this will be key number 4, 5, 5, okay, 6, 7, 8, 9, 10, 11, and then up to 12. And then I can simply wrap all this around a box to show that this is one server. So all these buckets you're seeing happen on one server. I'll say maybe this is server 1. Have this in mind. You can have it in your mind that all servers will have something like this. I can duplicate this, okay, and drag it down to represent another server. I'll say this is server 2, but we don't need this because of time, okay? This is server 2, but let me just quickly undo that so that we work with only one. It will make it easier for me to illustrate it. Now, the first step, like I've said, is to divide the key space into buckets. And a bucket is used as the root level node to maintain a limited depth of the tree. So all you're seeing here is one server, and one bucket is used as a root level node to maintain a limited depth of the tree. Now, once the buckets are created, we can now hash each key in a bucket using a uniform hashing method. So I can use a different color and say we can hash this key to something random, okay? To a hash, because a hash is simply a string which is very random. Let's say we are hashing to something like maybe 3, 1, 3. We hash to maybe to something like maybe 4, 1, 1, okay? Hash this other one to maybe 1, 1, 0, okay? And this happens for all the keys, okay? So it may take some time to do the hashes for each of these, but you get the idea. All the way up to 12, each key in the buckets is hashed, okay? The goal is to create a hash key in a bucket using the uniform hashing method. So when we are done with this, the next step is now to create a single hash node per bucket. So I'll copy this whole thing and drag it down to illustrate that. So I'll copy this whole thing again. Okay, copy it, paste, and then drag it down again, create some space, then illustrate and show you what I meant. So for every bucket, we create a hash node. So from this bucket, we have a hash node that represents the hash value. Not represents, but maybe stores the hash value is a better word. So for example, for this first bucket here, we can hash it, okay, and then keep its value in a hash node. So I'll say here we have a random value, maybe 6, 9, 0, 1. Then the same thing is done to this other bucket. Okay, we hash to get a random number, which is simply a hash. Do the same for this bucket. We hash and have a number. We do the same for this other bucket. We hash and we have a number or a hash. Maybe I can delete this gibberish and make it more real by putting a solid real value. As simple as that. Now, the next step is now to build the tree upwards till the root by calculating hashes of the children. Okay, understand this. The first step was to divide, okay, the key space into buckets, and we are using 4 for this illustration. And the bucket is used as the root level node to maintain a limited depth of the tree. The second step is that once the buckets are now created, we hash each key in a bucket using a uniform hashing method. Then the third step is to create a hash node per bucket. And the fourth step is to build the tree upwards till the root by calculating hashes of the children. Now, let me try to illustrate that quickly. I can copy this one here, okay? Or maybe not copy, but quickly draw. So it looks like something like this. You can have these two, okay? And we hash right here. Okay, so this is another hash node, okay, with its value. Then here we can have another hash node with a hash registered. Then we have the final one, which is the root with another value. Maybe I can put something here being the last node or the root. And again, this happens for every server. Okay, think of it that way, right? So once this is done, then we go ahead to do comparisons. Okay, because this would happen between at least two servers. So let me try to copy this and replicate and drag this on this other side and maybe just make it smaller. Okay, so we have that here, and then we have this other one on this side. Also make it just smaller. Wow, that's broken, but you get the point. Okay, I wanted them to be side by side, and ideally this second one would also have different keys and different values. Now, the next goal is to compare the two macro trees. Because for now we are dealing with two servers, and we start by comparing the root hashes. If the root hashes match, then both servers have the same data. But if the root hashes do not match, then the left child hash is compared with another left child hash in another tree, followed by the right child hashes. And then you can traverse the tree to find which buckets are not synchronized and synchronize those buckets only. That is how it works. Now let's look at the system architecture diagram next. Now let's talk about the architecture diagram. Do you remember the ring that we talked about in the beginning? This hash ring is still fresh in your memory, I assume. Now, like you see, it still has the 8 nodes because we're starting to count from 0. And the main features of the architecture are the following. Of course, I've mentioned the hash ring itself and the nodes. They're part of the architecture. But maybe it's best to mention the entire flow from the beginning in order to communicate the components. Now, the first one is the client or the client, and I'll draw the client. So we have here the client, and this client simply communicates with the key value store through simple APIs, and that is via what we defined in the beginning. So client sends requests and gets back responses. Do you remember what we discussed at the beginning? We said that the client simply performs either a get request by passing the key, or the client can perform a put request by passing the key and then the value as an argument. Simple, right? I hope that did not leave you memory. So this is the client. And then after that, we have a node, which will be the coordinator node. And this node is responsible for acting as a proxy between the client and the key value store. I'll choose node 6 to be that coordinator node. Then, like already you know, the nodes are distributed on this hash ring using consistent hashing, like I mentioned at the beginning of this video. And this system, like you know, is completely decentralized, meaning that we can add and move nodes automatically. Data is also replicated at multiple nodes. We don't have any single point of failure because every node has the same set of responsibilities. Okay, now what does a node do? Just to remind you, I will maybe copy this circle here and have it down here. Expand it. Let's see what a node can do. Of course, I'm sure you already know this. This is sort of like a reminder. A single node can do the following. we know that a node is number one, a client API. This looks very small. Let me expand it. So we have a client API. We have node being able to perform conflict resolution. A node can also help us detect failures. A node can also help us to do failure repairs. Okay. And a node also acts as our storage engine. In case you expand this, then you make sure that your node or every node performs everything which every other node can perform. This design you're looking at explains what happens after a write request is directed to a specific node. And these designs are actually based on the architecture of Cassandra. So here's what happens. A write request is persisted on a commit log file, and that is the very first step. Then after that, we have the data being saved in the memory cache. So this is the second step. Then we have that when this memory cache is full, or if it reaches a predefined threshold, then data is flashed to the SS tables. So this is step 3. Now you might be thinking, what is SS in full? It simply stands for sorted string table, the sorted list of key value pairs. Now, if you're interested in this, you can research more about it. After data is directed to a specific node, the system first checks if the data is in memory. If the data is not in memory, then the second step will be to check the Bloom filter. So Bloom filter is used to figure out which SS tables might contain the key. Just think about the Bloom filter as an efficient way of looking for the correct table. Then after that, the next step is to return the result of the dataset. And the result of the dataset is then given to the users. So this is how easy we can describe the read path for what you're looking at right now, or simply our key value store when a request, not any request, but a read request is directed to a specific node. We have studied a lot. Feel free to watch as many times as you need in order to understand everything. And I want to thank ByteByteGo for sharing such an important web page where I studied this. They have so many pages where they explain several things about system design and system design interviews. I encourage you to check their website and read. If you like me, I enjoy reading sometimes, and it's one of the best ways to learn tech. So go and read. This is not sponsored. This is me just appreciating what they have because I learned a lot from their website. See you in the next video.